Alright, hello everyone, and welcome to the first POPX Introduction tutorial. In this tutorial, I'm going to explain the basics of POPX and show you some common workflows and explain the general idea behind POPX. Let's get started. So, I'm assuming you already installed POPX inside your TouchDesigner project, and if you will open the OP Create dialog, you will see the POPX family over here. POPX stands for POPs extension. Basically, it's an extension for the POPs, the point operators that TouchDesigner recently released. And the focus of these operators is to make the transformation, deformation, and simulation of geometry in real time much more efficient and easy to use. So POPX are divided into five main subtypes. We have the generators that generates geometry, whether it's just a regular geometry or a packed POPX geometry, which we will look and explain what is it during this tutorial. We have the falloffs. The falloffs basically defines weighting, subactual weighting, um, on our instances or on our any geometry. The modifiers modifies the and changes the transformation of our instances or our geometry, and they can also modify, for example, color or any other attribute that we want. The tools are mostly utilities operators, and there are some tools that are related also for controlling the simulations. Uh, and the simulations are basically kind of like a standalone part of POPX. Most of them are basically just solvers that solves some physics simulations, but you can also build complex system with the simulation and with the help of, like, for example, falloffs or any other tools here to enhance your system. So let's get started. Let's look at what is POPX geometry. Um, so typically in a TouchDesigner instancing network, if you want to copy some geometry onto, for example, a spherical distribution, what you will do is you will drop your geometry, for example, a box, and connect the geo to it. And now, for example, I want to distribute them with a spherical distribution. So I'm going to drop a sphere and I'm going to have it only the points and reduce the frequency. I will connect a null, and in the geo, in the instancing tab, I will enable instancing and drop it into the default instancing OP. I will reference the position for translating, and I have my boxes distributed in a spherical distribution. Now, if I want to scale them, I can create an attribute here that we will call scale, and I can reference it here on the scale, and let's increase it so we can see the boxes. Great. And actually I can also make the scale 3-dimension to control each axis of the scaling. So let me fix it over here to reference the correct three axes. And now I can scale them in any direction that I want. Now, let's say I want to orient them um, based on the orientation of the points over here. So I will go to the instancing tab number 2 over here, and I will reference the rotate to vector uh, with the normal. Now immediately you can see that our boxes are being deformed, and typically this is not something that we want. So I can change the order over here to rotate and then rotate to vector. And this will solve this. Now, if I want to translate those instances based on their local orientation over here, this is typically will require some transformation matrix math and a lot of stuff mostly people doesn't want to get involved with, um, and this is where POPX comes in. So to make the same thing with POPX, it's I think much more fast and efficient, and I would show you why. So if we want to do the same thing, I will drop another box and I will connect this box to the instancer. Let's toggle off the display here. Now the instancer takes geometry and basically copies it um, to any distribution that we are referencing over here. So the default is a grid distribution, but I can change it, for example, to a spherical distribution. And I can open the spherical settings and lower the frequency. And then I'm going to go to the instancing tab. And in the global transform, I'm going to scale my instances to see them better. Now, if I start scaling in any direction, you can see that immediately they are scaled in the correct way. Or to see it better, I can drop a visualize frame, which will basically visualize my local orientation axis. And now I can also see how I can translate them. So for example, if I want to translate them on the z-axis, it will be like this. Or for example, on the y-axis. And also scaling. Now, you can choose another distribution, for example, a radial distribution, and it automatically will change the orientation attributes inside the instancer, and you could translate your instances in the correct orientation. Now, the instancer can take multiple geometries that it can instance. So to do this, I can add another geometry. So I'm going to press the plus over here. And I need to insert another geometry, for example, a sphere, to the second input that was just generated. And you can see now I have a box and a sphere randomly on my distribution. And I can scale them individually or translate or basically transform each of those in geometry. So let's scale down the sphere, for example, maybe a bit more. And now, because we're choosing to indexing mode to be random, so we can play around with the seed to choose another random indexing, and this will choose between the box and the sphere. And I can also play around with the probability of each instance. So, for example, here I can lower the probability of the box and I will get more spheres. Or I can do the opposite. All right, so I can also choose between the indexing mode to be a order, for example. And you can see this will basically make it like a order. For example, we have the sphere, the box, the sphere, the box, just like that in a pattern. And I can choose between a different sorting over here. So I can change the sorting to be random again, maybe, or a proximity to point, for example, and reverse it or shift it. Um, and let's actually do it. No change. And let's look at now the output of the instancer. So as you can see, the output is actually just some points and it's not the actual geometry. But those points contain all the information and attribute that the POPX system needs to basically generate the actual instances. So we have the position, we have the normal, the orient attribute, which is a criterion that defines the rotation. We have the point scale, the rest, which is the rest position, the scale, the up vector, and it's going to generate a POPX falloff, which will be used by the falloff operators and other operators, and you can change it. And we have the POPX ID, which is the ID of each instance, and the POPX index, which is the attribute that defines whether we're instancing a sphere, for example, or a box. Now, as you can see, if I connect those points here to the visualized frame, immediately I can see my instances. And this is because the instancer or any other POPX geometry will transfer this data onto the visualized frame or to any other operator. And I can go to the comment tab, for example, in the visualized frame. This is a page that every operator has. And I can choose to not render the primitives, for example. And this will not anymore instance those geometries. Now, in the instancer, you have two modes of instancing. You can choose to instance with the instancing. So this is using the built-in instancing of TouchDesigner. And it's typically much more efficient to use this if you're going to instance lots of copies. But the downside is that it's not using a matrix to basically instance. And if you want to have more accurate deformation for each instance, I would typically use the copy to points option over here, which will basically generate the same geometry. You see there's no really any effect, but internally it's actually deforming and transforming real geometry and not just with the instancing, built-in instancing of TouchDesigner. So if you're um, working with lower set of instances, typically copy to points and instancing won't be any difference, just that the copy to points can deform in a much more accurate way. Now, if you want further transformation of your instances, you can use the transform modifier, for example, and this acts like a transform pop, very similar to the, oops, sorry, to the transform pop, but it's going to basically transform your instances and not the whole geometry as one geometry. So I can scale them whatever to any size I want and translate them, and it will also always be in the local space unless I'm toggling off the local space. So if I'm toggling the local space, so you can see now they are not anymore translated in their local space, and you can see now I'm toggling on the do falloff, but currently my falloff is actually going to be 1. So if I plug in a POPX that a pop to that, so I'm going to choose the POPX falloff, and I can see the falloff is 1. So every instance is going to be scaled at the maximum value. And later on, we're going to look at falloffs and how we can basically use them to apply transformation and changes to our instances based on this falloff. Let's clean the network a bit. Okay, so another generator that I want to show you, which is a very powerful one, is the explode. So the explode takes any geometry, for example, let's grab a sphere. And if I connect it to the explode, what is going to happen is the explode is going to basically split my geometry into instances. Let's display it. So based on the partition method, for example, the primitive number or the clusters, I'm going to get instancing based on the method. And if I want to see it, I can visualize the pieces over here. And now you can see that each primitive of that sphere becomes an instance. And a better way to actually see it is to plug it into the visualize frame here. And actually, I'm going to reduce the frequency. And the visualize frame, you can see, is going to place the axis of the local orientation frame of each primitive. And if I'm using a transform, let's connect the transform here to the explode. And start playing with the scale, so you can see that each primitive is going to be scaled or translate. Currently I'm not in local space, but I can turn it on. um so yeah, so this is a very powerful tool, and you can also play with the orient, so you can choose not to orient them based on the orientation of this sphere, and more options about like how to orient them. You can use a costume up vector, invert the normals, or invert the up, and this will have an effect, different effect on your local orientation. Now, in the explode, you can also choose between the uh, clustering. So if I choose clustering, this is going to generate clusters of primitives that will be basically act like one instance. So currently I have 10 clusters, and I can, to see it better, maybe I can not generate the vertex normals. Actually, let's do it. And now I have clusters of primitives, and I can also translate them and scale them. So basically, it's kind of like splitting your geometry into pieces. And you can obviously play with the number of clusters. So I can go higher and maybe increase the frequency here. All right. Now let's move on and actually build uh, a small system that contains a falloff and a transform, any modifier. We'll start with the transform modifier because I think it's easier to see. So I'm actually going to use the instancer, and I'm going to have a grid distribution. Let's open the grid settings and maybe scale it like this, and maybe let's add more more instances. Now I will use instancing for this example, um, because I think it's much more efficient. Now let's choose to create a falloff, and let's start with the shape falloff, which is very common and useful. So I'm going to connect the instancer, and I'm going to display the shape falloff. So the shape falloff has some shape types over here that you can basically apply a falloff based on them. And to see the falloff, you can go to the falloff tab over here. That each falloff operator has this falloff page, and you can preview the falloff, and you can choose which kind of like coloring you want. Let's go with the infrared. Now you can see that I have the linear guidance over here, and I can maybe scale it like this, and I see that it's creating like a gradient, and this tells me that the purple instances are having a fall of 0, and the red ones are getting a fall of 1. And if it's confusing you, you can go to the costume, and if it's black and white, it's kind of much more understandable. So we can see that the black ones are having a fall off of 0, and the white one are having a fall off of 1. Now you can play with the shape over here, for example, a spherical shape, and maybe smooth this with the transition range and scale it down. So after creating a fall off, we can now plug in a transform modifier, for example, and start transforming based on this falloff. So you need to have the do falloff parameter on and choose the right falloff. So on the falloff, actually, on the falloff tab over here, you can see that you can choose between a combine operator, and if it's currently set to a set operation, it's going to basically set the falloff that we created onto the attribute name that we are pointing over here. So I'm going to choose the same name over here, which is POPX Falloff. And for example, I can scale my instances, and you can see the effect uh, is that the falloff is controlling the intensity of the scaling. I can maybe also translate them or rotate them. And yeah, I think this is like a very basic example. Obviously, you have lots of falloffs that you can use for. For example, the attribute falloff takes any attribute and creates a falloff out of it. So, for example, the default is the point index. Um, and I can choose between, like, for example, the position on the x-axis, and let's visualize it by toggling on the preview falloff, and you can see that we got something. Let's make it black, and I can also play around with the remap. So each falloff has a remap um, page over here, and I can basically fit it and use the auto input min max to kind of like make it a bit more smooth. And you can see it's created a falloff based on the x-axis. So the more the instances are on the positive x-axis, they're going to be scaled or translated. Another nice, I think my favorite falloff is the infection falloff. So the infections falloff is basically a small kind of like solver. Um, and if you connect your instances into the infection falloff, let's look at what's going on here. You can see that you see some green selected instances, which are the seeds. So if you go to the seed, you can display the seed selection, and this is going to be the start of the infection. This is where the infection is going to start propagating, and you can play with the scale, and you can also plug in or reference the seed pop over here to control many seed points, or connect it over here. It's the same thing. So I will visualize the falloff, and currently the falloff is all 0. But if I initialize my infection over here and press the start, hopefully it will start propagating. And if it's not, I need to increase the search radius, maybe more. Let's not display the seeds. Yeah, so we need to increase it quite a bit in this example. So you can see that my falloff is basically propagating. And I can also um, enable the dissipation rate. So for example, I can have like dissipation, and if I enable the reinfection, so it's going to basically continue infect instances that are already got infected. So let's start it again. Maybe increase this dissipation rate and maybe lower a bit the threshold over here. And let's connect it into the transform and see the effect. Nice. Now, a nice thing we can add to this is that currently it feels to me a bit more, a bit sharp, the way that the instances are moving. So I can plug in a Spring Modifier between the infection and the transform modifier. So the Spring Modifier can basically apply spring effect to the position, rotation, scale, or any other attribute. And this is what I actually want. I want to apply a spring effect onto the falloff that is being created by the infection. So I'm going to connect the infection falloff into the spring modifier. And actually, I'm going to create also a keyboard in to just um, reference it in the infection start pulse and the spring start pulse, because a spring is also like a small solver. Here I'm going to choose to um, apply the spring to other, and I'm going to choose the POPX Falloff, which is the same falloff that is being generated by the infection. And if I connect it into the transform, and let's start, press 1 to start the pulse, you can see that we have a much more smoother kind of springy vibes to the movement. And actually I want to scale it down here. Okay, now what I also want to do is actually, I don't want the edges to be affected by the transformation. So I'm going to actually grab this shape falloff over here, and what I want to do is to basically multiply. Let's look at it better. I want to multiply this spherical falloff with the existing falloff that I have over here. So I can choose here on the falloff tab on the shape falloff to combine operation to be multiply. And let's actually look at it. So you can see now that the falloff is being cut only, like being basically multiplied by the spherical distribution, and the edges are not affected. I can maybe make the transition a little bit more bigger like this, maybe less. And if I connect it to the transform and display this and press, yes, press 1, so I can see that the edges are not being affected. All right. Let's also look at more stuff here in the POPX family. So for example, I can also um, drop a randomize modifier, and I want my instances to be in a random kind of position a bit. So I'm going to randomize their position like this. Let's look at it for a second, but I feel it's like too much, so maybe I will lower the amount over here, and I will connect it to the infection. And now let's display the final results. All right. Now, to finish this tutorial, I want to explain a concept that is basically applied to any POPX inside uh, your uh, your network. So, what I'm talking about is the apply attribute POPX. So, the apply attribute basically is very similar to, I would say, the copy to um, point. Where is it? Copy. Yeah, the copy pop, sorry, which basically takes a geometry and copy it based on a template points. But the apply attribute is doing this for the POPX geometry, which are basically the packed geometry that we create with the generators. So for example, if I will take a null here from my instancer, I have my packed geometry, and I can connect it into the apply attribute, and nothing happens because I need to feed in template points. So I can feed in the end of our of our transform of our like system over here of POPX. And if I display the apply attribute, you can see that it's going to apply everything, every transformation and rotation to our uh, points over here. And I can choose whether to use the a falloff maybe, or a, if I don't want the translation to be affected, so you can see it's only the rotation, or maybe I don't want rotation, I want only scale. And you can do this for the pivot. You can make it in local space or not, and you can also choose a falloff for this. So if I create a falloff for that particular set of POPX geometry, the effect will affect only it will transfer, basically the applied attribute will transfer the transformation only based on the falloff. So for example, I can connect the attribute falloff that we created over here, and maybe let's do the rotation and translation, and you can see that only the side that is wider is going to be um, affected by our transformation from that system. So the apply attribute, basically it's the core of any POPX, and this is a tool that you can use if you want to basically work, for example, on a regular um, regular points, apply some simulations or transformations by your own, and then basically apply those uh, to a POPX geometry or any geometry that you want. Um, yeah, so I think we will finish this tutorial uh, at this point, and this is going to be just one part of the introduction, and in a later future tutorial, we're going to look at more modifiers, more falloffs, and more tools. And also, we're going to touch also the simulations. They will have their own series of tutorial. So thank you for watching. I hope this was useful for you, and I'm excited to see what you will create with POPX. Thank you so much, and see you in the next tutorial. Bye bye.